Okay, gentlemen, this is section 5.3. We're going to be solving trig equations. I wanted to give just a few general notes before we get into examples here. Note one, your answers should be in radians unless otherwise specified. Note two, we're going to give our solutions as general solutions unless there's a specified domain. And I'll clarify that on this first example. General note three, the steps to solving trig equations, are generally going to be isolating the trig function, and then you're going to use your unit circle to find the initial solutions. Okay. All right. So with that said, let's do a couple examples. We'll start here with example one. And so here's what I meant by general solutions. This says solve, and it does not give us a specified domain. So we're going to give our solution in general terms. And so step one is going to be to isolate our trig function. So we're going to collect like terms by adding sine to both sides. Right? So now I have 2 sine x plus root 2 is 0. So let's go ahead and isolate our trig function now. So we'll subtract over the root 2. We'll divide both sides by 2. And we'll say sine x equals negative root 2 over 2. Right, so this is where we're going to go to our unit circle to find our initial solutions. So I'm looking for where sine is negative root 2 over 2. So we're going to remember that the sine is the y-coordinate on our unit circle here. So when sine is negative, that means the y-coordinate needs to be negative. So it has to be in quadrant 3 or 4. I can see right here at 5 pi over 4, sine is negative root 2 over 2. And also in quadrant 4, at 7 pi over 4, sine is equal to negative root 2 over 2. So these two angles. All right. So those are our initial solutions. So 5 pi over 4 and 7 pi over 4. So I'm going to say x equals 5 pi over 4 and x equals 7 pi over 4. And so I said those are initial solutions because, yes, the angle 5 pi over 4, which is the angle measured from here around to here, is a solution. But also, if I went all the way back around and end up back here, that's a coterminal angle. That's also going to be a solution. And I could do that infinitely many times. All of those are going to be solutions to these equations. So notice each time I go around, that's a full rotation. So that's a full 2 pi. So I'm going to say generally the solution is 5 pi over 4 plus any multiple of 2 pi, any whole number, or I should say not whole number, positive or negative integer multiple. So n is a member of the integers, and that z just stands for the set of integers, right? So if I added 2 pi, or if I added 4 pi, or if I added 6 pi, that would also be a solution. And the same goes for the 7 pi over 4, right? The 7 pi over 4 is this angle from here all the way around to here. But if I did another full rotation, that would also be a solution. So I'm going to do the same thing and say plus 2 pi n. So there's really infinitely many solutions. So we call this the general solution. It's essentially, here's the pattern to get any solutions. Okay. Try example 2. All right, we're going to take the same tactic, which is we're going to start by isolating the trig function. So I just want to get tangent by itself on the left-hand side. So I'm going to add 1. So we have 3 tan squared x equals 1. Divide by 3. Tan squared x equals 1/3. Then I'm going to take the square root of both sides, remembering that when we introduce a square root, we need both the positive and the negative root. So I'm going to have plus or minus. Square root of 1 is just 1. Square root of 3 is square root of 3. There we go. So I've isolated my trig function. And again, we're going to come up with general solutions here because they don't specify a domain to find the solutions in. So let's go to our unit circle. Okay, we're going to remember that tangent is sine over cosine. And it's plus or minus 1 over rad 3. So we'll go ahead. Sine is the y, cosine is the x. So if we want it to simplify to 1 over rad 3, that's going to be this one here, right? So it'd be 1/2 over root 3 over 2. So times 2 over root 3. And we'd end up with 1 over rad 3. All right. So one answer is pi over 6. We've got the same idea here. Since it's plus or minus, we've got 5 pi over 6. We've got 7 pi over 6. And we've got 11 pi over 6. Okay, so we have 4 initial solutions because of that plus or minus. So like the last example, we could take all 4 initial solutions and just add 2 pi n to them, but that's not as efficient as we could be. One thing we can notice is that this pi over 6 and this 7 pi over 6 are only a distance of pi apart, right? That's pi. And same for 5 pi over 6 and 11 pi over 6. Those are straight across from each other, so they're a distance of pi apart. So I can essentially break this down to 2 cases. Instead of adding 2 pi n, I can take each one of those and just add pi n, and I'll hit all my possible solutions, right? So I'm going to start with the pi over 6. That's my first general solution. So pi over 6. And I'm just going to add pi n. And that's going to hit every possible solution for those 2 general solutions, right? So illustrate again. If I added pi to pi over 6, I'd be here, which is a solution. If I added another pi, I'd be back here. Add another pi back here. So that's always going to hit those general solutions. And now I want to do the 5 pi over 6 and also add pi n. So 5 pi over 6 plus pi n. And that covers all of my general solutions in total. So this is my answer. All right, let's try another factoring example. Okay, in this case, we have 2 different trig functions. So what we're going to do is try and just move everything to one side of the equation, get it equal to 0. So I'm going to have cotangent x times cosine squared x minus 2 cotangent x. So I'm just subtracting over that 2 cotangent x. So that's equal to 0. All right, know that we have a common factor of cotangent, so I can factor that out. And now I have cosine squared x minus 2. And now that it's in factored form, I can separate the factors and set them independently equal to 0. So cotangent x equals 0, and then I'm going to have cosine squared x minus 2 equals 0. We're just going to try and solve those individually. So I'm going to start with this cosine squared x. If we add 2 and then take the square root, so I get cosine x equals plus or minus root 2 here. If we try and go to our unit circle, remember cosine is the x coordinate. We'll notice that the biggest cosine ever gets is 1, and the least it ever gets is -1. And root 2, if I look at the absolute value of that, root 2 is greater than 1. So this does not produce any solutions. So there's no solutions to this one. All right. So now let's go back over to our other equation, which is cotangent x equals 0. Remember that cotangent is cosine x over sine x, right? Those are just our quotient identities. And so this will happen when cosine is 0 and sine is non-zero. So cosine is the x coordinate, sine is the y coordinate. So this happens at pi over 2. And down here at 3 pi over 2. So there cosine is 0 and sine is either 1 or -1. All right, they are not specifying that we need to find it within a certain domain, so we do want to find a general solution. And we can actually get this with one initial solution because these are exactly pi apart from each other, right? So I'm just going to use the pi over 2 as my initial solution. So we'll say x equals pi over 2, and then just plus pi n, and that covers all of our infinitely many solutions. Okay, example 5. Sorry, I skipped one. Example 4. Solving an equation of the quadratic type. So note that this one, they do give us a domain to solve this over. So we're not going to write the general solution. We're only going to find the solutions that are between 0 and 2 pi. All right, back in 5.1, we practiced factoring quadratics that had trig functions in them. One technique you can use if you just want to make it a little simpler looking is do a little substitution. So I'm just going to let u equals sine x, and I'm going to say 2u squared minus u minus 1 is 0. We'll go ahead and factor that. Let's start with 2u in both sets of parentheses. We're trying to multiply to make -2. Trying to add to make -1, so that's going to be it's going to be -2 plus 1. And we'll divide out whatever we can. That's going to be 2. So I'm going to end up with u minus 1 times 2u plus 1 equals 0. So putting it back in terms of sine, that's sine x minus 1 times 2 sine x plus 1 is 0. And then we'll separate those and set them independently equal to 0. All right, so I get sine x equals 1, and I get sine x equals -1/2. And in this case, we're going to find all the values of x for which this is true between 0 and 2 pi, so just once around the unit circle. So when sine is 1 or -1/2. All right, in this first quadrant, sine is all positive, but it's 1 at pi over 2. So that's my first solution. Sine is still positive in the second quadrant, third quadrant, sine is negative. Sine, notice, is negative 1/2 here at 7 pi over 6. And it's also negative 1/2 here at 11 pi over 6. And that's once around the unit circle. So 7 pi over 6, 11 pi over 6. And those are all the solutions that are between 0 and 2 pi. All right. Now we're going to practice getting this equation to be a single trigonometric function. We're going to be using our identities to do that. So note that we have sine squared and cosine. The easiest one to replace is going to be the sine squared because we can use our Pythagorean identity, right? So we know that sine squared plus cosine squared is 1. So if I isolate sine squared by subtracting cosine squared, I get that sine squared is 1 minus cosine squared. And so now I'm just going to replace sine squared here with 1 minus cosine squared. So it's going to leave me with 2 times 1 minus cosine squared plus 3 cosine minus 3 is 0. Now we have a quadratic that's in terms of a single trig function. We can solve it basically the same way we did our last example. So first thing I'm going to do is distribute the 2. I have that 2 and that negative 3, so those are going to combine to make negative 1. Just to simplify this and get it looking a little prettier, I'm going to multiply both sides of my equation by negative 1. So that's just effectively going to change the sign on everything on the left. I'm going to have 2 cosine squared minus 3 cosine plus 1 is 0. Do a little quick substitution, just replace cosine with u. So I have 2u squared minus 3u plus 1 is 0. We'll go ahead and factor that. All right, what multiplies to make positive 2 and adds to make negative 3? It's going to be minus 2 minus 1. And then I'm going to divide out the 2. I'm kind of going to do this all in one step, and I'm going to replace u with cosine. So I have cosine x minus 1 times 2 cosine x minus 1 is 0. Go ahead and separate those and set them individually equal to 0. So cosine x minus 1 is 0, and 2 cosine x minus 1 is 0. So I get cosine x is 1 and cosine x is 1/2. Okay. Again, they're not giving us an interval to find this over, so they're not specifying a domain. So we're just going to find the general solutions. So one is cosine 1. Cosine is 1 only at 0 and 2 pi. So basically, any coterminal angle with this, 0 and 2 pi, that's going to give me the solution to cosine x equals 1. So I can say 0 plus 2 pi n, but I don't really need to say 0 plus 2 pi n. I can just say 2 pi n. So there's my first one. And then cosine x is 1/2. So we're going to have cosine is the x coordinate, so it's 1/2 here at pi over 3. And it's also positive 1/2 here at 5 pi over 3. There's not really a way I can get both of those with one equation, so I'm just going to generalize it to two equations. So I'm going to say pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. There we go. That's my general solution. All right, last example. I'm going to show you guys how to solve multiple angle equations. So this is when we have a multiplier on our angle. Like this is cosine 3t rather than just cosine t. So we're going to start by doing a substitution for the multiplier on the angle. I'm going to let theta equal 3t. Then we're going to go ahead and just solve that equation for theta to start. So 2 cosine theta minus 1 equals 0. All right, so isolate your trig. So I'm going to add 1 divided by 2. Cosine theta is 1/2. And I'm going to generalize solutions here. So we're going to go back to our unit circle. Other way. So cosine theta is 1/2 at pi over 6 and 5 pi over 3. Right? So we basically just did this one. So I'm going to write two general solutions. So theta equals, not pi over 6, I'm sorry, pi over 3. I was looking at sine there. We're dealing with cosine. So pi over 3 and 5 pi over 3. So I'm going to write theta equals pi over 3 plus 2 pi n, and theta equals 5 pi over 3 plus 2 pi n. All right, so now we're going to take those equations and we're going to replace theta with its equivalent, 3t. So I'm going to get 3t equals pi over 3 plus 2 pi n, and 3t equals 5 pi over 3 plus 2 pi n. I'm going to isolate the t. So I need to divide everything by 3. So dividing by 3 is the same as multiplying by a third. Divide this by 3. Multiply this by a third. This should say 2 pi n, not 2 pi over n. By n, divide that by 3. Okay. All right, so my general solutions are now this. So I get t equals pi over 9 plus 2 pi over 3 times n. T equals 5 pi over 9 plus 2 pi over 3 times n. All right, now I specified a domain for this one. So I want all values of t that are between 0 and 2 pi. Remember, n has to be an integer. Integers are whole numbers, negative and positive. But I'm only looking for between 0 and 2 pi, so I'm going to start with 0. We're going to plug in 0 for n. If I plug in 0 for n, not there, in the t one, rather. Here. So if I plug in 0 for n, I get pi over 9. Pi over 9 is definitely between 0 and 2 pi. If I plug in 0 for n here, I get 5 pi over 9, which is definitely between 0 and 2 pi. And then we're just going to increase n by 1 and keep plugging it in. And the solution we get, as long as it's between 0 and 2 pi, that's going to be part of our set of solution values for t. The next thing I would plug in for n would be, for example, 1s. If I plug in 1 for n, I get pi over 9 plus 2 pi over 3. 2 pi over 3 is what? 6 pi over 9. 6 pi over 9 plus pi over 9 is 7 pi over 9. If I plug in 1 for n in this bottom one, I get 6 pi over 9 plus 5 pi over 9, which is 11 pi over 9. That's definitely less than 2 pi because 11 over 9 is less than 2. Okay, then we go back in, plug in 2 for n. Okay, that's 4 pi over 3, which is 12 pi over 9, plus pi over 9 is 13 pi over 9. Still less than 2 pi, right? 18 pi over 9 would be 2 pi. Plug in 2 to the bottom one. 12 pi over 9 plus 5 pi over 9 is 17 pi over 9. Now we're almost at 2 pi. If we plugged in 3, we'd be over 2 pi. So this is our solution set. All right. On to your group work and delta math.